welcome to Visiting Lecture today with Chandigarh Group of Colleges, Punjab from India. Welcome to the Honorable Mr. Rahul Dev Singh as an Assistant Professor Department of Computer Science and Engineering. And the topic today is data structure. Yeah, and today's session is being live streamed on the Universitas STEKOM YouTube channel also. And now I will read over agenda this afternoon. First, we will start class presentation by Mr. Rahul and continue with the Q&A session after already presentation. And the next session is time for documentation, take a picture, and last time is closing. Okay, let's begin.
Ma'am, excuse me, remove your clothes and show your boobs and I will fuck you, ma'am. I fuck you asshole. Remove your clothes, show your boobs and show your PC. I fuck
Okay, and we will start for this class today. Delivered by Mr. Rahul. The time is yours. Thank you.
Fuck you, fuck you.
Can we mute all the participants?
Yes, sir. Already. I think it's a hacker join.
Yeah. So should I start?
Yes.
Yeah. Thank you. So, dear participants, as ma'am told you, my name is Rahul Dev Singh, and today I am going to give some views about concept of data structures. Right. So, first thing I want to know if I am audible to you or not clearly. So, I hope I am clearly audible, right, ma'am?
Yes.
Yeah. Thank you. Just a minute. Sorry for interruption. I will take one more minute and then I will start.
Yes, sure. It's not.
Yeah. I hope now settings are okay. And okay. So, what is the data structure and why it is required? Before understanding it, we need to understand what is the data. So, data are basically a collection of raw facts which are organized in a some way that is meaningful for us. So it can be continuous or a discrete and as a term of values. So we can say that in short that data is a collection of discrete or continuous values that contains information describing the quality, quantity, fact, statistics and other basic units which are meaningful or simply sequence of some symbols that may be further interpreted in some other way. So to understand it, first we can see this data type, right? So data can be text, audio, charts, videos, tabular form, or in a form of images, right? So it depend on us how we are going to interpret this data, right? So if we understand data, then we can divide them in different parts. For example, we have this number 5000 here, right? So this number is a atomic data. 5000 rupee or $5,000 have a individual meaning in itself. We can't divide or separate any element from this data. That's why it is called atomic data, right? Second thing is called composite data. So what it is composite data? Composite data basically created by the combination of some other parts. For example, this is a phone number where +91 representing a country code, then 11 is representing city code, and then the other number shows individual's phone number, right? So we can divide data in two parts, obviously, in atomic one and composite one. And on the basis of their application, we can also say that this is the text data, audio data, chart data, tabular data, video data, or image data, right? So when we understood that what is the data, then we can describe what is the data structure. Data structure is nothing but a way of organizing the data in some fashion so that later on we can be accessed it and queried or even update easily and quickly it, right? So once we know our data and we know our application, then only we can decide which data structure have to be used there, right? So data structure is nothing but a collection of values that where the values can have relationship among them and can have functions, some kind of functions can be applied on them. So each one different data structure is basically independent and can be used on different applications. So it depend on us or on our application that which kind of data structure we have to use, right? So as I already explained that data is a combination of atomic and composite in meaning and their relationship. So if you want to if you are able to see this, that data structure can be designed in a single way or it can be nested one. Okay, so why data structure is basically important? So data structures are essentially component in creating fast and powerful algorithms. Algorithms are basically backbone of any application, and data structure is basic component of those algorithm. It fuel them, right? So to create fast and powerful algorithm, we require data structure. They help to manage and organizing data so that it will make our code clear, concise, and easier to understand, right? So data structure can make difference between a okay product or in a best project. Uh, just a minute, right? So for example, imagine you want to design or you want to design an application to store different contacts in your phone book, right? So to store that context, you required name, phone number, emails, address, and many more things. So there are multiple ways to store this kind of data, but you have to choose which kind of data structure is suitable to store this kind of data in a contact book of your phone number, phone basically, not number. So data structures and algorithms are two important topic in computer science. A data structure is a way to organize and store data in a computer. But the other side, an algorithm is set of steps or instructions that are used to solve problems for your computing. For example, sorting, searching, and other things, right? We can classify data structure on the basis of three different categories. First one is called shape or layout. So on the shape or layout, we can say data structures can be divided in two parts. First one is linear and second one is non-linear data structures. If we talk about size or flexibility, then data structures can be divided in two parts, static and dynamic one. And if we want to implement them on the if we want to classify them on the basis of implementation, then we can say that we can classify data structures on the basis of concrete concrete and abstract. So in a concrete way of implementation, we know how we are going to implement it, but in the abstraction part we never know what kind of algorithms or way are used to design that particular data structure. For example, you are using C programming language, right? Or C++ programming language. So in C and C++, there are no stack based implementation in the basic compiler. There are libraries available, but I'm talking about the basic compiler here, right? And you want to design your own stack data structure. So for that one, you have to use either pointer based link implementation or you have to use array. But how arrays are implemented on C compiler, you don't know about that, right? So that kind of implementation is abstract for you. And when we talked about the size and flexibility, then for example, again in the same programming language, C and C++, if you want to create an array, then at the time of compilation, you have to mention the size of that array. If at the time of compilation, compiler don't know about the size of array, it will throw an error. That means the size of array at the compile time is static, right? But somehow by memory reallocation functions, we can change the size of array and other data structures. So if the size of data structure is fixed, then it is called static. And if we can update the size of the data structure, then it is dynamic one, right? Linearity and non-linearity. Let's discuss it next slide about that, right? So what are the some common data structures? Array. So as you can see in a one dimension, arrays are linear one, right? This is the all the elements are arranged in a single way. So that is called one dimensional array. If we have collection of single dimension arrays in the another dimension, that is called 2D array. And same for if we have collection of 2D array and we want to extend that in collection in another dimension, that is 3D array, right? So we can extend that array up to nth dimension theoretically, right? The another data structure, common data structure is the list, where we can add nodes dynamically in pre-designed list, where we have always a head node which have address or reference of next upcoming nodes. and each and every node have link or reference of next upcoming node. So by that way, we can arrange all the uh, data in some linear way. So array and list both are the example of linear data structure, right? And the third one is a stack. Stack is basically a linear data structure where in and we can access these data structure from a single point. So this single point is called top of that stack, where we can push elements in that stack, and then on requirement we can pop these elements from that linear data structure. So in a stack, the element inserted first always pop in the last. So we can say that this is the first in last out based data structure, or we can also say that this is last in first out based data structure. So it depends on your understanding. You can say that this is a philo data structure, FILO, or LIFO, right? It depends on your interpretation. So first in last out or last in first out, right? Now, the fourth one, that is a queue data structure. It is again a linear one, but it has two ends. First to insert data, and the second one to remove data or to access that data, right? So the operations of inserting data in queue is called in queue operations, and the operations to access that data or remove that data from the queue is called DQ. It works in the first in first out manner. Which element inserted first, that comes out first. So we can say that is FIFO, right? First in first out data structure, right? Okay, so these are the basically all linear data structure. All these data structures are linear. Now time to understand about non-linear data structures. For example, tree. As you are able to see this figure, where we have a node P. P is the parent node, or you can say this is the root node, because there is no parent exist for this node. But all other nodes are either the child or subchild of that root node, right? So our every node is either a root node, leaf node, or intermediate node, where they have a key that is a data for that data structure. So is as in this example, you can see that root node have a value P. So here P is the key of that node, right? And the node P have two childs, Q and R, and so on. So this is a hierarchical model of data structure, right? So we can say that this one is non-linear one, right? And the another one is a graph. Graph is some nodes that are connected in a non-linear way. So where we have multiple vertices, where these vertices are connected by some edges, right? So tree and graphs both are the non-linear data structure, right? And there hash tables are also, which are basically stored the indexes of some data. We will discuss them later, right? To understand one point, which one is more important, linear one or non-linear one? So if you read your textbooks or your curriculum, you will find out that your most of the part is focused on the linear one, array, list, stack, queue, and many other linear data structures. But if you try to search applications around you, then you will find out that this word is not linear at all. maximum number of applications are non-linear one. So obviously tree and graph have more applications to implement, right? Now, I already discussed about abstract data type models where I told you that you in abstract data type you never know the implementation part of that data structure, that how it implemented, but you directly used it. For example, I already told in a C and C++ programming language, if you want to implement tree, graph, stack, queue kind of data structure, then you have to use some pointer type of pointers or array to implement further data structures. But you never know that how C compiler implemented array and pointer itself, right? Now, before going deep in data structures, first we need to understand how they are different to each other, right? So to understand that, we need to understand that what are the basic necessity or what are the basic parameters by which we can choose different data structure in different applications, right? So there are two basic parameters to choose some data structure in some problem. First one is the time complexity and the second one is the space complexity. But as a computer engineer student, we always focus more on time complexity because cost of CPU is much more in comparison to memory, right? So time complexity is nothing but an algorithm that measure time complexity in seconds, and we always design a function for some kind of input that tell us that what is the maximum time can be taken by that algorithm on some kind of CPU. Okay, for example, we have this data, right? We can say that this is an array where numbers are stored in a linear way. For example, 99, 81, 93, 22, 57, and so on. But if we want to sort that array, then this is the sorted order of this data. But how much time it will take in this sorting mechanism, right? So suppose if we want to sort them by comparing each and every element by their neighboring element, then what is the worst case? If this array is already sorted but is reverse order, then it will take many comparisons. For example, there are multiple algorithms, right? So for you, I basically choose some algorithms and data. Okay, I have an array of 50 elements, right, where data is arranged in random order 37, 23, 42, 47. I purposefully choose a static array so that we can compare between multiple algorithms, right? So run it. Okay, so there are multiple algorithms for the same problem: bubble insertion, quick selection, merge sort, hippify, cell, and counting sort. So let's see on a bubble sort how many comparisons are required to sort this data. As you can see here, number of operations, right? So for that 50 elements array required on that random data, total 1225 comparison, right? Let's check for some other algorithm. Same thing, right? For example, we choose selection sort. And for selection sort, it takes 1271 comparison on the same data, right? So number of comparison changed when we changed algorithm. But what if we choose some other algorithm? For example, suppose I choose here Happify, right? Happify is a very fast algorithm. For the same data, it required only 248 comparison. It is basically approximately less than 5 to 6 times, right? So choosing an algorithm for particular application can be very critical. Eh, so always need to understand different algorithms, their complexities, and then according to requirement, we should choose that one. So before going further, we need to understand how can we calculate time complexity for any algorithm. So for that, we always represent time complexity in a form of fn, function f for any given set of input n, right? Now, for example, here we have a code, and that code is in C programming. We have a function where we have an array of 5 elements, right? 5, 4, 3, 2, 1. And we just want to traverse on that. So size of array is if n, then to traverse on that array required a constant time, right? But what if we want to check linearly each and every condition? For example, here we have a loop for I is equal to 0 to I is smaller than 1000, I plus plus. That means where at the first time I will have value 0, and that value is increased by 1 in each and every step up to 999. That means value will increase how many times? 1000 times, right? So we can say that this function fn basically runs at the equivalent value of n. So this is the linear time. If we want to plot this thing, then we can say that y is equal to x, where x is greater than y is equal to 1, right? So what happened? Just a minute. Y is equal to x, where x is greater than and is equal to 1, right? So for the each value of x, time complexity is increased linearly. in the same way, right? Second, what if the value of I increased by value 2? Then again, in that case, the value will plot in a linear way, right? It will return a straight line to us, right? That's why it is called linear time, because we are increasing or decreasing that function by a constant value, right? Now, suppose we have a loop where we are increasing value with the multiple of some constant. Here, notice that thing. We are increasing values here by adding something, right? Or subtracting something. So number is increased in a linear way, right? But in the another example, numbers are increased in a multiple of 2 or by division of 2. So if we check that if there are total one function run one time, then iterations are 1. If the value of 2, then 2 times. If the value of 4, then 3 times, and so on. So it is equivalent to enough log base to form. Y is equal to log x, where the value of x is greater than or equal to 1. Now, let's compare. For the value of x is equal to 14, what is the cost of an algorithm that take linear time and the cost of the algorithm which runs in log n fashion, right? Nested loop. Nested loops are loops where one loop dependent on the another loop. So the cost of iterations are equivalent to total cost of outer loop or total count of outer loop multiplied by total count of inner loop. So if you have two functions here or two loops, for example, for I is equal to 0 to I is smaller than 10, I plus plus. For j is equal to 0 to j is smaller than 10, j plus plus. Then, point to be noted, for each and every value of loop A, for each and every value of loop A, loop B will run 10 times. And how many times loop A will run? 10 times. So outer loop A will run 10 times, and for the each run of loop A, loop B will run 10 times. That means the statements written inside the loop B will run how many times? 100 times. So total iterations in this particular nested loop will be 100, right? So in this case, if we say that the outer loop will run n times and inner loop will run n times, the cost of that function is n square times, right? So let's draw for n square. C. For the value of 20, this is the point or cost of log n. This is the cost of n, and this is the cost of n square. And in the same way, suppose we have a function suppose we have a function where function outer loop is increasing in a linear way and the inner side loop is increased in a fashion of log n. So we can calculate cost directly. The total cost of this is what? N. And the total cost of this loop is log n. Right? So what is the total cost here? N into log. Right? Now you know very well which algorithm you should choose on the basis of size of your data. Right? You can also see for different cases. This is the quadratic. So in a case of logarithmic, you have cost log n in a linear n, in the linear logarithmic n log n, and quadratic n square, in polynomial n to power k, and exponential c to power n, and in a factorial n factorial. Suppose you have value of n equivalent to 10,000. Okay, you have 10,000 inputs. If you are using an algorithm which results in log n time, that means you require approximately 14 iterations. That means estimated time for any computer is in milliseconds for that algorithms. But if it runs in a linear time, it required time in seconds. If you are using linear logarithmic, it again calculated in seconds, but in a quadratic one, it will take some minutes. In a polynomial case, it will take hours. In exponential and factorial, we can't calculate right now because it depends on machine to machine. Let's check it. Is it true figure or not? For example, I write here a code to calculate time for different condition, right? Or run it. Okay. So as you can see, first one is calculation is log for logarithmic function. Okay. For logarithmic function, we are going to run it first time for value 1 to 20,000. Then 1 to 40,000, 1 to 80,000, 1 to 1,60,000, and so on. Right? Then we will calculate total time it takes. Nearly zero time for this computer, right? Nearly zero. And if you check carefully, my compiler is saying that it takes zero time even for 2.5 million calculations, right? But what if I am checking that one on linear function? Oh, sorry. Uh, I give wrong value. For linear function, I have to type 2. Same values, but as it is taking time in linear way, for 20,000 inputs, it is taking 0.0025 seconds. For 40,000, 0.0030 seconds. And so on. This is the graph for linear one. Let's check for same values on linear logarithmic function. Now we have to wait. So there are so many calculations and it is taking time, right? As you can see that for it is continuously calculating things, right? Okay. So this is the time in second. So for 2.5 million inputs, it takes nearly 33.71 seconds. Now, same data, if algorithm calculating in log n time, then time is nearly zero for all inputs up to 2.5 million data, right? And in a case of linear logarithmic, it is taking for 2.5 million calculations 33.71 seconds. Now, as a computer engineer, you have to design systems for big MNCs, right? And they have to calculate billions of data in a limited time frame. Then, for that, you have to choose any optimized algorithm for that particular data. So, to optimize that data, you need to choose a particular data structure. Data structure is a backbone of computer science because if your data is not organized in a right way, then you are not going to handle it in a right way and your algorithm will fail. So, each and everyone can write code, but writing a code in an optimized way is very difficult or required more practice, right? And we are not going to test all other parts because we know that 33 point something seconds required for linear logarithmic function for 2.5 million data. Then what about quadratic and polynomial and exponential and factorial functions, right? It will take lot of time for calculations, right? If you want to check, then for example, let's leave it because I hope you understand the point, right? For all different algorithms, if it requires log n time, then the graph is in this way. If it requires n time, then this n log n, n square, n cube, and so on. Right. See, so now we understand the importance of time complexity of any algorithm, right? Generally, we use either linear or non-linear data structures to solve any problem. So, before discussing about any particular data structure algorithms, I choose the most used data structure array. And I hope all of you know about how array works. Array is a linear data structure where we can access data from any index directly, right? So for that, I choose an application of sorting so that I can show you how different algorithms can change scenario in different applications, right? So there, for that purpose, I choose sorting application. We can divide sorting algorithms in two parts, internal and external. So internal sorting algorithms can be divided again in three different categories: insertion based, selection based, and exchange based. So bubble sort and quick sorts basically runs on the exchange based model, and selection sort and heap sort work on the category of selection, and cell sort and insertion sort based on the insertion, right? We choose this application because this is the one of the most fundamental application of any data structure. And I hope you are aware about the fact that sorting is basically the first algorithm which is implemented by compiler designers, right, in computer science field. Okay, so when we want to sort any data, it can be sorted in a stable order, stable and unstable methods, right? What is the difference between stable sort and unstable sort? For example, this is our data. Here, as you can see, 202 number indicated the value green, 212 again indicating yellow, and 212 is indicating value blue. When we sort on the basis of these numbers, this data, if the order of data against that number maintain the same order, then that is called stable sort. For example, in the next one, purple, first green, second yellow, and third blue, then blue, right? So it is called what? Stable sort. Wherever, and another side, you can see blue was the third one, green was the first, and yellow was the second. But that order is distorted here, right? So data is sorted. There is no problem in sorting, but we lose our initial order, right? So that kind of algorithms called unstable sorts, right? Okay, so now we know stable and unstable sorts. They are two way of sorting algorithm, right? Okay, so one of the most fundamental sorting algorithm is bubble sort in computer engineering. Okay, so bubble sort algorithm basically do nothing, but it compares that particular element with their neighboring elements. Okay, so it requires a lot of comparison. Obviously, we already checked that first example where bubble sort required total 1225 comparisons on the size of 50 elements, where data is arranged in random order in those arrays, right? So we understood that this algorithm is not suitable for large data, but this is one of the most fundamental algorithm. So we are going to discuss it first, right? So how bubble sort algorithm works? So first thing, we pick an array, store the elements. When we have that array, then we first pick first element of that array. Then compare the current element with the next element. Then if current element, and I never says that this is the sorting in ascending order or in a descending order. So if we don't discuss it, so in that case we always, if it is not given, then we always assume that we are talking about ascending order, right? So in a third step, if the current element is greater than the next element, then we swap them. Then after, in a fourth point, move to the next element, or you can say set next element as a current element, and then repeat step 2 and 3 until we reach on the second last element of that array. Okay, then when these process completed, then repeat step 1 to step 4 again for all elements. So basically, it check if an array have n number of elements, it will check n square times for all the elements are sorted or not. So let's check the working of this bubble sort algorithm. Suppose I am choosing an array of 8 elements, and I don't want to give them. So I choose bar type of layout and randomly picking some number. For example, 44, 67, 23, 78, 12, and 7, and let's 87. So how many elements there? 1 2 3 4 5 6 7. So one more, 39, right? So these are the 8 elements in our array: 44, 67, 23, 78, 12, 7, 87, and 39. So see, this is our array in unsorted way, right? So what should be the right way? 7, 12, 23, and so on. So which one is our first element? This 44, right? Uh, just a minute. Okay, there's sorry. Okay. Okay. So first element is 44 here, right? And last element is 39. So what our algorithm said, if the current element is greater than the next element, then swap it, right? But as the current element is here 0, just I'm checking for annotation tool. So 44 is basically smaller than 67. So that's why there is no swap will happen, right? Check for 44 with 67. 44 is already smaller than 67. So no swap. Then the current next element will become current element. So the current element is now 67. So 67 is going to be compared with the next element, that is 23. Now 67 is greater than 23. So swap will happen, right? Right. So value swapped. Now, which one is the current element? Index 2, because earlier index 1 was the current element, right? So current value is what for index 2? 67. So index 2 value is going to compare with the index 3 value. 67 is again smaller than 78. So no swap is going to be done here, right? Now, in the next step, which one is the current one? Element index number 3. 78 is greater than 12. So swap will occur here, right? And so on. So this is the first round. And after first round, we can observe that the largest element or largest value is already sorted in the last of the array. So we will run this process again from the index 0. Second last element sorted. Repeat this process again. And now array is sorted. So you see, it required lot of comparison, right? And if we change number of elements, right, in array, then number of comparison changed. So again, I am showing the same visualization to you for bubble sort where 50 number of elements we have. And array sorted, right? It take too many comparisons for that. I hope the working of bubble sort you understood, right? So if array is already sorted, then bubble sort required total time because no swap is going to be done there. But if in a case of average or worst case, it required n square time, right? The another algorithm that is basically take n square time but a different approach is a selection sort. So in a selection sort, we always select a element and then on the basis of that selection we perform swapping, right? So for selection sort, first we choose first element of that array, then start finding from that place for minimum element in unsorted partition of that array, then swap with that minimum element with the first element, or if you implemented algorithm in a different approach, then with the last element you swap that minimum value, and move the boundary of the sorted partition by one element to the right. And again, repeat step 2 to step 4 until the entire array is sorted. Right? Let's check it. Okay, 44, 65, 12, 87, 5, 33, and 26, and 8. This is an unsorted array. We are going to perform selection sort. So let's choose first element, then start for the smallest one. As I said, we can implement it by two way, either selecting largest value or smallest value, right? So if you are choosing the largest value, then you will swap that with the last element. And if you are implementing it for choosing smallest value, then you will swap it with the first element of array, right? Again, we will perform same operation and so on. Now 33 is largest. And now array is sorted here, right? So bubble sort and selection sort works very differently, but they require nearly same number of comparison and square, right? And to save time, I'm going to pick one another algorithm, that is merge sort. Merge sort is a general purpose algorithm which utilized basically conquer divide and conquer strategy or approach, where we divide data on the basis of some parameter and start dividing till further requirement, right? So there are two most famous sorting algorithm on this approach. First one is the quick sort and second one is the merge sort. Merge sort is the easiest one in comparison to quick sort. That's why I choose for this lecture. So to perform merge sort, first we need to divide array nearly equivalent halves, right? If you have a even number size of that array, then you can divide them equally, right? But if the size of array is odd, then you can't divide it equally. So that's why I said nearly equivalent, right? So starting to divide the array into halves, then performing this process recursively up to where there are basically one single element in the array. Once we reach there, then we start merging these subarray back together in a sorted way. Then on the requirement, we move the boundary of merged portion from one element to right side of it. And repeat step number 2 to step number 4 for entire array. Let's See this. So, okay, 8 elements are randomly choosing values 34, 65, 2, 78, 33, 24, 65, and 1. Check it. Okay. So this is our array 34, 65, 2, 78, 33, 24, 65, and 1. We have indexes from 0 to 7. That means total 8 values we have. Now, according to algorithm, first we need to divide this array nearly equivalent halves up to there only one element exists in array, right? So see, we choose our array, entire array, and then divide them in equivalent half. 34, 65 to 78 in first sub array, and the remaining 33, 24, 65, and 1 in another sub array, right? Then recursively, we first choose first sub array and then again divide it. Two halves in the same way, 34, 65 in a one array, and 2 and 70 and 78 in the another subarray. Then choose first one. Now, there in this subarray, right now we have a single element in a array, right? Now we are going to be compare those single elements. So 34 is smaller than 65, right? So now 34 is going to be placed first and then 65. Now time to perform same operation on the second part. They divide, then time to compare them. 2 is smaller than 78, so 2 will be placed first, then 78. So now we have two sub-arrays where each sub-array have two elements, right? So now time to merge them. So first element will be compared with the first element, and 2 is the smallest one. So 2 placed first, then 34, then 65, then 78. Now this part of array is sorted. Time to perform same operation on the this part of subarray. 24 was the smallest, so it picked first, then 33, and then same way 65 and 1 subdivided. Then 65 is larger than 1, so 1 will be picked first, then 65. Now these two halves are sorted. Time to merge them. 1 will pick first, then 24, then 33, and then 65. Now we have two sorted subarrays with 4 elements. Now time to merge these two subarrays into master array. So going to compare first element with first element. So 2 is greater than 1. So first will pick first. Then 2. And by this way, that array is sorted. So let's compare by a code. We know that for the bubble sort, this array required 1225 comparisons. We checked that. And for the selection, it required 1271 comparisons. So now time to check for merge sort. Only 335 comparison, near about to less than 4 times in comparison to bubble and selection sorts. So hence, now you know better that choosing an algorithm can be very critical for any data structure, right? We implemented all these applications on array data structure, but whatever other data structure you used to implement these sorting algorithms return you respectively equivalent results, right? So for the comparison purpose, I provide time complexities of different algorithms on this slide. So as you can see that either best, average or worst, selection sort always demand n square time, right? Whereas the bubble sort on the already sorted array required only big O n time. And merge sort sorted all the data in n log n time. So thank you very much to attend this lecture. If you have any query, then you can ask to me. Hello. Hello.
Yeah, yeah, thank you so much for your presentation. Yeah, for all participants, if you have any question for the speaker, please add them to the chat or you can raise your hand. We will wait until 3 minutes. Just a moment, please, sure. Thank you. Yeah, for first question, we have question from Mr. Abdul. Yeah, good morning, Professor. I have a question about data structure. Could you explain the main difference between an array and a linked list in terms of how data is stored and accessed? The question already right in the Zoom chat also, sure.
On the chat box.
Yes.
Uh, okay. First thing, as I already told in that lecture, array required static storage. So at the time of compilation on many data structure, many programming language, you have to mention first your size of an array. Yeah, this is okay that you can access any index directly from that array, right? But in a case of list-based implementation, you have to provide pointers or reference of that particular node. So sometimes it is very tricky to access particular kind of node. So at the background in ADT, it is taking more time to access that data. But in array, you can't implement real world problems directly because it is a linear structure, right? For example, suppose there is a requirement to gather data from different telecom uh, towers, right? Telecom towers are not connected in a linear way, they are in a graphical. So to design a graph, you have to implement that graph using different independent points so that you can access those nodes easily or in a faster way. So it depends entirely on your application. Either it is in a hierarchical way or in a graphical way. Then you have to you should implement that by a list method or a pointer based method. If it is a completely linear one, then you can implement that by array. If size is also fixed, if size is not fixed, then please choose linked list.
Okay, thank you and for answering. And then the second question, I have some question about data structure that I like to clarify. Could you explain the difference between array and linked list? The question from Mr. Farik. Thank you.
As I already told that arrays are static data structure. As I'm showing the from my presentation one slide. There are different data structure. So yes, array and list both are linear data structure. So we can say they are similar kind of data structure. But if we check them on the basis of their flexibility, then array is a static one and the list is the dynamic data structure. Right? I hope it helps you.
Okay, thank you for
Okay, thank you
answering.
for
I think it's very clear answer from Professor. I guess no one else asking again. Yeah, before I close this event, for all
for
participants, please open your
please
camera.
open your
I will take a picture on the count of three. Okay, 1, 2, 3. Okay, another one. 1, 2, 3. Okay, thank you. Thank you for your kind cooperation. Finally, we come to the end of visiting lecture today. We would like to thank you for Mr. Rahul Dev Singh for the wonderful information and sharing your knowledge. We hope this information will be beneficial for all participants. At least we hope to have more collaboration in the future with Chandigarh Group of Colleges, Punjab, India. The visiting lecture for today and here. We hope to see you soon. Thank you and have a nice day. Thank you so much for Mr. Rahul. Yeah,
Thank you very much.
goodbye. Yeah, bye bye.